that one of the questions from 15.3, number 10, if you can remember what it was like a sphere, and then they bored a cylinder through it. Remember that guy? And it was saying that something wasn't right about it. And so what I have got here is the entire working for that question. I couldn't find my working for the last time, or I would have just brought it up. So I'm not sure what I did wrong. So let me explain the gist of it. If you take a sphere and you bore the cylinder through it, if you look at it vertically above, what you get is a disc that looks like this, right? And we're essentially being asked to find what the volume of this shape, which is basically a sphere with a hole cut through it, would be. This region ends up being this fella. So you might say, well, where does this guy and this guy come from? Can you imagine looking at a sphere from above? Wouldn't it just be x squared plus y squared equals 25? So that's where this comes from. And then the cylinder is this one. So if you look at it, this shape from above, this is basically what the cut on the floor would look like, because you need to know the region that is called either D or R, depending on the question. And so this is this fella. And the function that we're going to use, the Z guy, is a rearrangement of this fella, which gets me that. And now I'm going to set this thing up. And I think I didn't do this, so that might have been my mistake now. If I calculate the volume of this surface, or using this as my base area, I need to double it. And that I'm pretty sure I forgot to do. Now, you might say, well, why do I need to double it? If I only integrate this and the bit above it, can you see I only get the top half of the shape? So the doubling is just to get the whole answer. So if you parametricize, or if you turn this into polar form, it's 2 to 5 because of this. And it's a whole circle's worth, which is this. And the 2 because you want the top and the bottom. This fella here ends up being essentially a U sub. And that's the answer. And I checked this answer, and it is the correct answer in the homework, so I know it's right. So I'll just leave that page for a few moments. You can always go back and watch this video later tonight if you need to see the details. So if you're frantically writing, I wouldn't bother unless you really want to. You know, just freeze the picture. I think I've talked long enough for you to be able to have a window to see it, so you can stop at it. Are we good with that question now? I think, yeah. Anthony, when you look at my working, because this is the version I had to do because I couldn't find the old one, has that fixed any issue that you noticed when I was doing it?
For me, it did, yeah.
Okay, so hopefully that's fixed the problem. We are moving on, onwards and upwards. I think we covered everything, I hope, in polar that you need to worry about, but if not, you can always tell me tomorrow and I can go over something. So what's our next section? We're going to look at what's called the centre of mass. This is applications of double integrals. And this is evidently something that is very important to engineers and people in the sciences. And essentially what you're going to do is find the coordinates of the centre of mass of any kind of, I think they call them laminas or laminates or something, which is just a fancy name for. Can you imagine you've got a shape, two-dimensional, that's all we're doing right now. And on this shape, it's not got a fixed density. Can you imagine at some ends it's quite dense, quite heavy, and at other parts of it, it's a bit fainter, right? And so what you do is you create a function, or you have a function called the density function. So imagine this was my density function. What that is saying is that at any given coordinate x, y, the density would be equal to whatever this is. So, you know, density is a measurement of mass per cubic meter or whatever, right? So what would the center of a mass of an object that has this kind of shape look like, or any shape? How do we calculate it? Well, the total mass of this object, if that's all you wanted to know, is how much would this piece of metal weigh, right? And then you might think, well, you can't get a two-dimensional piece of metal. Well, could you imagine it had the same thickness? Then wouldn't the mass be, you know, the same as the double integral of this guy? In other words, the area. So if you do the area of a density function, what you're essentially getting is the mass of that object at a unit thickness. So how do you then calculate the coordinates? So can you imagine that there's some point in here called x bar, y bar, which is we call the center of mass, evidently. And that center of mass is quite an important thing to use, because I think what you do in engineering is, if you have an irregular shape, it makes dealing with it really difficult. But if you find its center of mass, can't you treat it as if it was just a single point in space and do stress calculations and moments and all sorts of stuff using the center of mass as a way around that problem? So they want to know it. X bar, the x coordinate of the center of mass, is 1 over m, which is this guy. The double integral over the region D, that's the region D, of x times the density function, or y times the density function. I'm just double checking that I got that right. Yes, I did, for the change. Now, me personally, I couldn't care less. The way I look at this is, if you tell me how to do something, then give me a function, give me a region, and I'll find the center of mass for you, right? So tell me the density function, tell me what the shape is, and I can find it. Now, for the engineers amongst you, you're more interested in the conclusion, whereas I'm kind of more interested in the process that gets you there. So that's just a matter of preference, right? So I'm not going to fake, oh, that's really cool, I want to find centers of mass, because I really don't. But it's cool math. I like that part. So, oops, I got my thing stapled, probably shouldn't. So I've got a whole number of questions we're going to try and get through. I'm going to set up quite a few of them, but I'm not going to do them all the way to the end because they're quite long. I think you've got something like 6 or 7 in your homework, so at least that's something, right? With the exception of the last question, they're very similar to each other, you know, the process at least. So here goes. Right, I'll keep that guy handy for a little while. And here's my first question. Here is a piece of metal. It's got this shape. They designed it by telling me the 3 coordinates. Here is my density function. I want to find the center of mass. If I was a gambling person, wouldn't the center of mass probably be somewhere, oops, you can't really see it with my finger in the way, right, where that black dot is? Which is what? 1, 1. Now, will it be there? Probably not, because in this density function, can you see that as x and y increases, the metal gets denser? So this piece of metal is quite dense at the corners here and maybe up here, and less dense at the origin. So how do we start it? Well, you find the mass, which is the double integral of the density function. Well, I'll call it dA right now. I need this guy to be written down in a form that's going to allow me to do a double integral. So I'm going to do it by finding the equations of these 2 straight lines. Because if I do that, won't I be able to go like this? And I'll be able to say, okay, it's going to be the integral from x equals 0 to 2, and y equals little guy to big guy, right? And I'll just repeat the 2xy, and I'm going to do the y's first and the x second. Right, that top guy, oh, that's 3, that's 2. What do? You go 2 along, and you go 1 down, so that's -1/2 plus 3. Does that look accurate to you? I'm doing it in my head. If you want to tell me I made a mistake, this is your chance. Would you agree this line here is you go 2 along and 1 up? So I'm assuming that's just what, 1/2 x, because it goes through the origin. Does that look good? Right, so top line, -1/2 x, add 3. Bottom, 1/2 x. I'm going to do an integral from 0 to 2. Oh, darn it. Can you pretend I did 2x plus 2y so I don't have to rewrite it? So 2x gets you 2xy, and 2y gets me y squared, evaluated from 1/2 x to -1/2 x, add 3 dx. So far, so good? Continuing that process then. It's 2x, -1/2 x, add 3, plus -1/2 x plus 3 squared. Subtract 2x, 1/2 x plus 1/2 x all squared. That times that gets me, it looks like -x squared. That times that gets me plus 6x. This guy gets me 1/4 x squared minus, what's that, 3/2. Take another -3/2, which I believe is -3x plus 9. That guy times that guy gets you x squared, so I'll subtract it. That guy gets me 1/4 x squared, so I shall subtract it. And we have that guy. Continuing. It's going to be the integral from 0 to 2. Let's collect like terms. Well, that guy kills that guy off, and that guy gets me -2x squared. This guy and this guy gets me, I believe, plus 3x. And the only number I seem to have is 9. Are we good? I'm just going to keep doing this until somebody says something's wrong. If you then come back in 10 minutes and say, hey, by the way, shouldn't that be 4x or something? If I was in the class, I would throw something at you. But since I'm not allowed to throw things at students, and being virtual is kind of hard anyway, I will just pretend that I did it correct so that we can continue the process.
Yeah,
So,
real quick,
yeah.
Shouldn't the slope for that top function be -1?
Here? Yes, but I'm not going to change it because there are too many lines.
Professor.
Your job is to catch me earlier. So we pretend that this was correct, so the process will continue the process. In fact, now that I'm going to do that, I might as well just keep cheating and pretend that I did that and it was 42. Because what we're really doing is walking through the process. The details are very important, but they're just going to slow us down if we go into too much. Would you agree, power rule, plug in 2, plug in 0, you'll get some number. It won't be 42, but you'll get some number. Right, which means then that we're kind of finished step 1. Step 1 is get the mass. So you want to get x bar. It's 1 over the mass, the double integral of x, the density function, dA. if this was correct, it'd be 1 over 42. The double integral would be the exact same start and finish every single time. And I will fix it here. So it should have been negative x had 3. And x times the density function, and we'll do the dy dx guy. Now I have 1 over 42. And I'm just going to multiply this all through. So what do I get? I get 2x squared plus 2xy dy dx. This guy gets you 2xy. And this guy, I believe, gets you xy squared. And you would replace the y with negative x add 3. And then you'd replace it with a half x. And can we just pretend that that entire mess could be foiled out, distributed, whatever you want to call it, collect like terms? Would you agree it'd be a power rule? Plug in x equals 2 and 0, subtract everything, and we're going to pretend that I got 84. So that would make x bar 2. If I did. So I'm just pretending that's 84. It's more time, this particular version, isn't it more time consuming than difficult? It's just got all these lines of working that eventually get you to the end. That's what I hope you see. So x bar is just 1 over whatever this answer is, the double integral of an x times this guy. And do you know what y bar is going to be? Look at the difference. So can you imagine me going through this entire line of working again with one major difference? That becomes a y. So can you imagine it would change here, it would change what you got, it would change everything because of that all the way through. It's not difficult, it's just time consuming. And let's pretend that I did it and I got 1. Then the centre of mass, if I went through the whole question from start to finish, was 2, 1. So all we need to do to solve this is basically follow instructions. Find this guy, usual way. Find this guy, and then this guy, and that guy, comma, that guy is the centre of mass that you're looking for. Are we okay with the process? Because I skipped a lot of corners and pretended I knew the answer to certain things. We could actually do it, but then that would mean I'd only get 2 questions done and we'd never get the course finished. So I'll just give you a taster of what they look like. Oh, darn it, where's my... Oh. I guess what I'm going to do for the rest of these questions is I'm just going to basically set up what this guy looks like. Because if I set up what this guy looks like, would you agree these two are really just almost the same question, right? Almost the same, right? In this case, you've got this curve and y equals 0, which ends up generating this fella. And the density function is 11 ky. K is just a constant. That's, you know, like 11 times 10y or something. So let's get the mass. So double integral of our density function, dy dx. Now, since I've got this region, the x's are going to go from -1 to 1. If you take a typical rectangle, these guys, don't you go from y equals 0 to the top, which is y equals 1 minus x squared? Are you happy that this double integral represents that region? Are you comfortable with where I got this, the -1 to 1 and the 0 to 1 minus x squared? We're good? Right. So, not a difficult fella to do, so let's find out what we have here. -1 to x equals 1. 11 ky with respect to y. Well, that's going to get me 11 halves ky squared, evaluated at 0 and at 1 minus x squared. That is going to give, in a few moments, the next piece of the puzzle. It's going to be 11 over 2 k 1 minus x squared minus nothing. Okay.
That should be squared.
Thank you. Welcome. Now, how would I tackle this? Me personally, whenever there's k's involved, or even multiples of k, pull the darn thing out. And then basically, that makes the k's kind of irrelevant, right? Now, whenever I get the answer to this, 42, won't I just go 42, 11 over 2k and get, you know, 212 11ths k or whatever, right? So it will not disappear forever. Give me the technique that I'm going to use to do this fella, because this is Calc 2 now. I can't integrate this. Say again?
U sub.
Do we need to use sub in this case?
You can just FOIL it out and then do power roll.
Yeah, FOIL it out and do power roll. If there was an x next to this, like an x 1 minus x squared, I might think about a u sub, but even then I probably would have just multiplied it out. So can we pretend I did all that? And I got 111 halves k. Because I did, right? I'm just making that part up. Isn't that going to be the m that goes here? Now here's something cool that's going to happen. You're going to have this guy, and then you're going to have an integral, a double integral, and to get x bar, you're going to have an x, right? The density function, right? The dA thing, right? This answer here is going to have some k's in it, right? So you integrate it, you do all this, and let's suppose that you've got 42k, right? Imagine that came out to be 42k. Do you notice that this k and that k will cancel? And 42 and this will come out, and what you'll get is 84 111ths. So even although the density function has a k in it, the x bar function, the k's will always cancel out, and you will be left with a virtual, an exact value. So whatever that really is. My gut feeling is telling me, based on this shape, that won't x bar probably be somewhere in the y-axis? So that would be interesting if it was. And Is there anything in this? Because I'm really only starting the question. I'm not really taking it to the end. But it's, in that process, I'll be comfortable. So, we've got some nods, so I shall move on. Here's the next one. We're taking this guy in the first quadrant, and this is all weird stuff. The density function is not given to you, although I've given the answer to what it's going to be. The density function has not been given to you. Instead, it's proportional to its distance to the x-axis. So why did I write ky when it's proportional to its distance to the x-axis? If you take a random point, isn't the distance to the x-axis your y-coordinate? And when you say the word proportional in physics and engineering, don't you mean that the formula is a fixed amount of that thing? So k times y. So that's how that was created. That is not in the homework. You have to create that. Suppose I had changed this word from proportional to its inverse distance to the xy, and I said inversely proportional to its distance from the x-axis. In that second situation, what would the density function be now?
K over Y.
So if you're not into physics, that is brand new stuff to you. But if you ever see proportional, it means k times the thing. If you see the term inverse proportional, it's k over the thing. Are we good? Right. While I'm on this, I'll come back to this question in a minute. Suppose I went and said to you that the density function was proportional to the distance from the origin. Now, proportional means the k, right? That's the k part. But in particular, what is the formula for the distance to the origin of a general point? So imagine that's xy. What is the distance of the general point x comma y to the origin? If that's xy, and this is 0, 0, what's the distance, d?
Square root of x squared plus y squared.
And that's what the density function would look like in that story. Suppose I went and said to you that the density function was inversely proportional to the square of the distance. To the origin. Now, it's inversely proportional means it's going to be k over somebody. What's the square of the distance to the origin?
X squared plus Y squared.
There are going to be some questions where the density function is described in this kind of terms. And so you have to be able to take inverse proportion or proportion, the distance to the x-axis, the distance to the y-axis, the distance to the origin, whatever it might be, and convert it into these looking guys. Are we good? Now, back to question 4. It's x squared plus y squared less than or equal to 49, and the density function that we're going to use is ky. So the rest don't matter. This is the region they're talking about, right? The mass is the double integral over the region D of the density function. We'll call it dA, right? That's the generic version. Based on what you see here, do you think this might be a candidate for using polar coordinates rather than sticking to the X's and Y's? Can you see that the math is going to be much easier in polar? Now, in polar then, won't this guy be r equals, well, I think I'll stick to my usual, theta equals 0 to 2 pi, and r equals 0 to r equals 7, and the density function is still ky for a few moments, and then it's going to be r dr d theta. Are we all comfortable about the general way in which you convert things to polar? Now, the only guy that's really needs to be fixed here is that y is not going to play well with r and theta. So what does y on its own look like when you make it polar?
R sine theta.
So can you imagine that the only fella that I changed here was k r sine theta dr d theta.
That should be an R squared.
And you're right, because that r with that r is going to come in. Is this a variable separable situation? Can I break this into two separate integrals?
Yes.
So I'm going to go theta equals 0 to 2 pi, and I'm going to give the k the sine theta. And that gives me an r equals 0 to r equals 7 and an r squared dr. Now, we can get the answer to both of these agreed. Right? Isn't that just a power rule? Isn't that just going to be negative k cosine theta? This fella is going to be 42k, right? I like 42k. So what's the difference going to be for x bar? Well, for x bar, won't I stick an extra x in there? And won't that be the calculation? And to get y bar, won't I stick in an extra y? These limits of integration will be the same. This will turn into r dr. Won't xy just be converted into r sine theta and r cosine theta? And won't y squared be converted into r sine theta being squared? So if you can get the answer to this fella here, you should be able to get these two as well. Ky with an extra x, ky with an extra y. And then just do polar on everything in sight.
So when I did the actual integral of the sine theta, I got 0. And that doesn't really work for this sort of problem. So that means
Did
the
you?
math would be
Well,
0.
okay, let's just do that little guy, right? So I'm just focusing on 0 to 2 pi. Let's pull the k out so it's out of the road. And we'll do a sine theta d theta. So if I integrate this guy, I get negative cosine of theta. Evaluated at 0 and at 2 pi. So negative the cosine of 2 pi, take away negative the cosine of 0. Cosine of 2 pi is 1, so that's negative 1. Take away cosine of 0 is 1, that's negative 1 plus 1. Oh, you get 0. You do? Right, what's this version of? Did I say this was question 4? Let me look at.
When you started this question, you said it was in the first quadrant,
First
but we also
quadrant,
do
yeah.
a full circle.
Oh, shooting space. Okay,
So it makes
that's
sense
why
that
you got 0.
it would make sense that it would be 0 because, you know,
Top
a
and bottom
circle.
cancel it. Yeah. Okay, so the only alteration I need to do is not use the whole thing, but only use the first quadrant, which pretty much just changes one integral limit, and that comes out nice. Well, I don't know if
Wouldn't 0 still technically be nice because the center of mass is at the origin?
well, unfortunately, the center of the mass may be at the origin, but m equals 0 won't make that happen because won't I have to do 1 over 0 over here?
Oh yeah, you're right. Yeah.
And that would be a bad idea. I guess the moral of that story is if this is ever 0, have another look, right? Because it shouldn't be. Is this allowed to be negative?
I would assume no. You can't have negative mass.
So for practical purposes, no. I would agree that negative mass is a bad idea. But I guess theoretically it could be negative. I could imagine a function that might generate a negative answer. Now, I have no idea how the physics people figure that out. But I guess it would mean that I have got an object that is lighter than 0. I have no idea. You'd have to watch a sci-fi movie to make that work, right? But of course there is one. If anybody knows of an old sci-fi movie, H.G. Wells and First Men in the Moon, there was a material called cavernite, which was painted on. It was a liquid. And it had the property that it blocked gravity. So in those cases, objects could have a mass that would be negative, because then they would float. And that's how they got to the moon. Useless piece of information, but it came to me, so I thought I would tell you. Let's do 6. We have a limited time. In this question, you've got half a guy, half a guy. You've got a donut, top half. The density function is inversely proportional to the distance from the origin. So that's where this guy came from. So let's calculate the mass. Okay, that would be its generic form. Let's turn it into, well, you tell me. Do you think that this is a very good candidate for polar? So I'm going to go 0 to pi. That'll get me the top half. And r equals 1 to 5, and that will give me the donut piece. K. Are you happy about k over the square root guy being inversely proportional to the distance from the origin? You happy about where this came from? So k over r times r dr d theta. And I am really quite surprised. Can you see why I'm surprised? The r's cancelled out, which I wasn't expecting, but it's nice. If I split this up then, won't it be the integral from 0 to pi of, and I'll give this a 1. And from 1 to 5, give this guy the k, so that's going to get me 5k, and that's going to get me pi. So I guess the answer is 5 pi k. It's a surprisingly nice question. Oh, time.
Wouldn't that be
It's-
4K?
Surprisingly, still nicer question. But 4K, 4 pi K. Right, I'm looking at people. Are you saying hi right now? Because a whole load of people just kicked in here.
Yes.
Right. So I won't need to say, will you all say hi? So anybody who hasn't said hi, will you say hi so you get added to the list? Are we comfortable with what this guy looks like, right? Okay, suppose I wanted to get x bar. Wouldn't it be 1 over m and stick an extra x there? Now, wouldn't that x turn into a r cos theta? And so it would have a knock-on effect all the way through. But essentially, I think if you know how to do the maths, aren't the x bar and the y bar going to look very similar, right? You're going to use the same integration, right? The same limits of integration. You're going to do the dr, d theta, and all that good stuff. You're just going to add one extra component, x or a y. And you already know what this number is, right? So that's going to be 1 over 4 pi k. And if you do it correct, the k's cancel. And I have no idea what you get, but the answer's 3 and 2, and there you would go. You'd be finished. I guess we'll find out later whether this is working when you actually physically get to do them. So hopefully you get to do some examples before I see you tomorrow. And if you have an issue, then we can go over some of those. So the last question, I'm just going to set it up for us. There are a thing called moments of inertia. Never done engineering in my life, not interested in ever doing it. But does anybody even know what the heck moments of inertia are? Because evidently you need to find them.
Yeah, we
I've
did work with
taken
this
the
in statics
classes.
last quarter.
I've
So
taken the
these
classes
things
with this
actually
done.
make sense to you, right? But to me, I just need to know what the formula are. And for you, if you're not an engineer, don't you just take a note of these formula? So if there was a test question that said, find the moments of inertia, wouldn't you just say, oh, you want me to get this and you want me to get that? And in this particular question, the region D is, oh, a rectangle. And the density function is given to us. So this is how I would set up Ix. How about x equals 1 to x equals 3? How about y equals 1 to y equals 4? Since they call it y squared, I will call it y squared. The density function is ky squared. And I do dy dx because of the order of integration. I would do a little bit of tidying up and then I'd be good to go. This is going to be ky to the 4. Could I just pull out the k away to the end? Right, just stick it out there so it's forget about it kind of time. This is variable separable, really, isn't it? Couldn't you just find this integral and then do that one? 1/5 y to the 5, plug in 4, plug in 1. No idea what you get. 213/7 made up answer. Okay. So I get Ix. If I want to get Iy, don't I just replace that by x squared? Variable separable, so separate them into two nice integrals. And I'll get, I don't know, 412/7 k. And what does I naught mean? Does that mean overall moment of inertia? Whatever it is, evidently you add these two guys together. So I would add these two guys together, and that would get me I naught. This is 600 and gone to my pretend answer. That guy. So that would be Ix. We pretend that would be Iy, and there's your I naught. What do moments of inertia tell you? those who've done it, what the heck are they? Just curious.
I literally do not remember. I've taken like 2 classes that had them, and I still really never got a straight answer.
When you're working with angular motion, they're like the equivalent of mass.
So, so when things are moving in a circular motion, there is some mass associated to the object that's moving that is changed by the circular motion. Because I'm thinking an object's got a mass due to gravity, but when a thing moves in a circular motion, that force of gravity, whatever you want to call it, is altered by the inertia. Is that kind of what it is?
Yeah, it kind of just tells you how much like torque you need to get something going.
Oh, so the word inertia is like in the English word that if something's got inertia, it's hard to shift. Right.
Yeah.
Right. Okay, so the moment of inertia is connected to shifting something. Does it shift in a circular motion, or you can shift it in any motion you like?
It's rotational motion, inertia.
Okay. And the reason you want to know this is because engines and moving objects, it's kind of a nice thing to know. I guess, okay. That's as good as I need to go. I probably went further into engineering than I ever want to go. We're going to leave at this point, Leah. I just